We're going to make a two-dimensional representation of the problem of aligning two sequences with gaps, indels. So let's say we draw one of our sequences horizontally. Basically, you could think of it as the x-axis. So I can just write some arbitrary sequence down here. Okay, so let's call that our first sequence. Maybe for the purpose of simplicity, I'll refer to that as the variable x. And then vertically, I'll draw another sequence, maybe that is somewhat similar but not identical. Okay, so now I'll draw something like something like that, and I'll call that sequence y. Okay? So this representation where we have two dimensions representing our pair of sequences is kind of useful because what it allows us to do is picture the alignment process actually as a path. So what do I mean by a path? Well, let's consider what happens as we step through our two sequences through an alignment process. So you'll notice, for example, that our two sequences start with the letter A. So we might say, well, maybe those two A's should be aligned to each other. So what would happen if we asserted that they should be aligned to each other? Well, in so doing, we would have basically taken those two A's out of the picture, right? And the next letters that we have to consider are now the following two letters, okay? So one way of drawing that as a picture would be basically as a diagonal move, which I'll draw with a diagonal arrow. In other words, we've advanced on both our x dimension and on our y dimension, and now we've arrived at the next cell representing the next two letters. So one way of kind of formalizing this picture would basically be to draw what we would call a matrix, where each of our letters basically is a separate row or column. Okay? And so when we enter a diagonal move in one cell, that basically means that we're now going to the next cell. Okay? The direction of the arrow is kind of arbitrary. There's kind of a convention, maybe for drawing it in this direction, for a reason that you'll see in a moment. Basically, that when we reach the end of our filling out our matrix, we're actually going to do a process that's called backtracking. It's basically like following the direction of these arrows to work out what the complete alignment path should be. But the whole idea that I want to express by this writing an arrow is simply, this means that we are matching A to A, and in so doing, now we end up in the next cell, which considers our two letters C and A, okay? All right, so let's follow that arrow or directional notation one step further. Now let's consider what we would do if we had an indel, okay? So just for the purpose of argument, let's say, oh, maybe I consider this C to be an insertion in this sequence relative to that sequence. So basically, I think that the next letter, G, actually should align against the A and skip the C. Okay, well, what does that mean practically? It means that basically I'm going to skip past this box and I'm going to go to the next box, okay? And we can consider that to be like a horizontal move whereas here we had a diagonal move. And that makes sense. Here we were advancing on both of our coordinates, whereas here if we just skip the C, we're only advancing on the horizontal coordinate while staying in the same place on the vertical coordinate. Okay? So we would write that following the same convention that we had there as a horizontal arrow. And so we could call that, for example, an insertion of our letter C in the horizontal sequence relative to the vertical sequence. Question?
Can you also go up instead of...
Yeah, exactly right. So the last remaining move to be considered is exactly what you just said. Is, oh, gee, what if we considered this A now to be an insertion relative to our sequence here. So basically now we're going to say skip the A, but stay at the same place in this sequence here. So we would draw that now as a vertical move like that, okay? And that would sort of take us up to this next cell up here, okay? So that's the basic idea. So the whole point of everything I just told you was that we can consider the problem of alignment to be reduced down to like a set of 3 moves. With these 3 moves, we can construct all possible alignments of our 2 sequences, right? So for example, if I considered this whole sequence, except for the last letter, to not align to that sequence, so I'm going to skip all these letters and then I'm going to align that A to that A, it would be like writing horizontal, 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 and then the last one I would do a diagonal, okay? So in other words, we can write an alignment by writing sort of a string of these 3 moves. You see what I'm saying? Any questions about the 3 moves? So the next thing that I want to draw from that idea is that the set of all possible alignments we could consider as basically being all the ways that we can cross over this matrix using our 3 possible moves. And so we can kind of get a intuitive or sort of back of the envelope feel for how hard that problem is by considering, for example, what is the scaling for the number of possible ways of aligning these 2 sequences as a function of the length, okay? So going back to this idea that, okay, let's say the length of both sequences is the same length, let's call it n, okay? What is the total number of paths across this matrix? How does that grow as a function of n, okay? So simplistically, one way of thinking about that problem is, you know, I can draw just about any path I want here by like saying, okay, I'll go diagonal, diagonal, then vertical, then horizontal, and I reach the other side of the matrix, I've completed an alignment, right? So one way of saying it would be that the total number of possible alignments is equal to the total number of paths using our 3 moves. Total number of paths across this matrix. So if we say, for example, that the number of rows and columns is just n, and at each step we have 3 choices, then the number of possible paths is going to be like 3 times 3 times 3 times 3, like n times, right? So that would imply that the total number of alignment paths would be something like order 3 to the n, which is horrible, right? That just is going to explode even faster than n squared. And even for a very short n, just becomes completely infeasible, okay? So this is a slightly more formal way of showing that adding insertion and deletion really makes the problem computationally harder, right? Because a moment ago we were saying that simply sliding the two sequences past each other was more like order n squared, where we didn't allow any insertion or deletion, right? Now we've added insertion and deletion, and we're getting a much more horrible computational complexity, more like order 3 to the nth power, okay? So insertion and deletion really makes the scale of this computational problem dramatically worse, okay? But we're not done yet. We are going to be able to squash that order 3 to the n actually back to order n squared if we can make a very simple assumption about our scoring, okay? So now I'm going to draw a picture of the scoring problem that hopefully will make that idea clear. Okay, so on the scoring, when we compare different letters of our sequence to each other, we can introduce a very, very simple assumption, which is simply that the score for any pair of letters only depends upon that pair of letters, and it doesn't depend upon anything somewhere else in the sequence. This is called the independent score assumption. Basically, the score for any pair of letters does not depend upon what you have somewhere else in your alignment. So one way of formalizing that mathematically would be to say that the total score for a complete alignment is just equal to adding up a set of independent terms, which are the scores for each pair of letters that you're aligning to each other, okay? So if we make that simple assumption, and we'll talk later about what situations that really fits versus does not fit, okay? But if we do make that assumption, we can simplify the algorithmic challenge for alignment quite a bit. And here's how. Basically what we can do is we can introduce this idea of a globally optimal scoring alignment. In other words, a path whose total score is greater than or equal to the score of any other possible path across the alignment. So I'm going to introduce a little bit of some symbols, basically. So let's say that we call a path just by the letter P, and let's say we introduce a function called S that represents its score. Okay, so P is some path across this matrix consisting only of our 3 moves, and S of P is the total score for that whole path. Okay? So then we would define a globally optimal alignment as being a path that I'll call P star, whose score is greater than or equal to the score of any other path P. Okay? So that means there's no other path that scores better than P star. Just to make the obvious point, if we want to find P star without any kind of intelligent algorithm, we're stuck with a computational complexity of order 3 to the n, right? Because we'd have to look at all the possible paths P, of which there are order 3 to the n, to see if their scores are greater than our claimed P star. And if none of them were, then okay, we found P star. Okay? All right, so now we want to simplify this. Let's use our independent scoring assumption in the following way. Let's say that we know the beginning and end of P star. So I'll call that, I'll call those positions B and E, okay? So let's say, just for the purpose of our argument, that the beginning of our P star was down here, and let's say the end of P star was there, something like that, okay? And now there's some path that represents some path that's P star. Okay, let's just say that's P star. So I'll just mark that, that's P star, that path that I just drew. Now let's consider some alternate path that goes between, let's say, some point in the middle and our beginning point, okay? So let's just designate some point on here. Let's just call this point, I'll call that point Q, okay? So it's some point in the middle of P star. It's on P star on this globally optimal path, but it's not at either end, okay? And now let's say there's some other path. Now let's see. I didn't choose my place very well there. Let's say that that's Q, okay? And then I can have an alternate path, like for example, that would be an alternate path, for example. So I'll call that alternate path, I'll call that P prime, okay? So the path going like that is called P prime, the path going like that is called P star. Obvious point, the path P prime and P star are the same from Q over to E, but they differ going from, say, B to Q. Okay, so now let's consider the score. We'll break it down into the two pieces going from B to Q and from Q to E. So what we're saying here is the score for B to Q on the P star path plus the score from Q to E on the P star path has to be greater than or equal to the score going from B to Q on the P prime path plus the score from Q to E on the prime path. Okay? So that just follows because independence, right? We have claimed that the score for the total path can just be broken down into separate pieces for the individual parts. They don't depend on each other, so it's just addition. Okay? Now, we said that Q to E, the paths P star and P prime are identical on that portion. Therefore, these two pieces, it's the exact same subpath, so it must be the exact same score, right? So we can just subtract that from both sides, and we're left with S from B, Q star must be greater than or equal to S of B to Q prime. Now that might seem like a very trivial conclusion to arrive at, but actually it's a profound change in the meaning of our condition. This is a global condition. We only know it when we're at the end of our whole path. It basically means we have to consider all possible paths in order to produce this condition, right? This is a local condition. This just means that anywhere in the middle of some path, if I have two possible ways of getting to this point, the one that has a lesser score than the other cannot possibly be P star, right? Because P star is the highest scoring path. What this condition is, this is what we would call a local condition. It's a rule that we can apply at any point in our alignment to eliminate paths that cannot possibly be P star, okay? And what it really translates down to is that when you assume independent scoring, that whenever you're trying to make a decision somewhere in the middle of your alignment path, and you have more than one choice, any of those choices that scores less than one of the other choices just can't be P star, okay? So basically what that means is at each point on our alignment, we can look at the three possible moves that arrive at that point. There's the diagonal, the horizontal, and the vertical. Each of them has a score. The one that has maximum score out of those three choices is the only one that I need to consider because it's the only one that could possibly be P star. Okay? So basically what this says is you might think that, we might make a compromise at one point where we say, oh, well, I'll accept a lower score here in order to get a higher score somewhere else. But that doesn't apply when you assume this independent scoring idea, right? Because the scoring here can't affect the scoring somewhere else, okay? So what that means is you always take the maximum anywhere in the middle of your alignment, okay? So that's what this local rule says. It says always take the maximum anywhere in the middle of constructing your alignment path. What does this get us? Well, the first point I want to draw your attention to is the fact that here in this whole layout we assumed we know this is the P star path and we're just making some decision in the middle of P star path. Well, clearly when we're making a decision somewhere here we don't know whether this is on P star or not. Okay? So what we're going to do is we're going to fill out the entire matrix applying this rule. We're going to apply that rule everywhere. Some of those points will actually be on P star and some of them won't, right? So what will happen is we'll have to fill out the whole matrix because you don't know which of the cells are actually on P star or not. When we fill out the entire matrix, then actually we're in a different situation because we can just look at what's the maximum score at the end of our matrix. Okay, that has to be the end, that has to be P star. Right? That represents the highest scoring path across the entire matrix because you can prove that if you follow this rule, you definitely will retain P star. You won't throw out P star. Okay, you'll throw out lots of paths that are not P star, but you won't throw out P star. Okay, so it's guaranteed P star will be represented in the final result once we fill out this entire matrix. We just look at the matrix, the highest score, and then now we're going to have to reconstruct P star by so-called backtracking. And that's why we have to write down the moves that we chose on each step while we're filling out the matrix, okay? So that's the concept. Now I'm going to actually show it to you by doing it on our matrix, okay? Any questions just about kind of the conceptual basis of, what is it that we're going to try to do as an algorithm and why? I think it'll become clearer when you see it just done in practice, okay? Well, before we go too much further into that, let's just consider what we've gained via this independent scoring assumption. How much work are we going to have to do to fill out this matrix in terms of this same kind of scaling factor? So we said that, for example, the enumeration of all possible paths was order 3 to the nth power. What would you think the computational work, number of steps or time for filling out this matrix according to this rule would be? How will it scale? If, say, both of our sequences are length n, how will the number of steps? N squared, exactly right. So what we've achieved here is we've squashed order 3 to the n back down to order n squared. There's a huge improvement in the computational complexity. So order n squared is something that's quite manageable. If n isn't too big, it'll eventually become impossible for us to, wait that long to get our answer. But for a whole large, up to a relatively large size, we can still do order n cubed, n squared. Okay, So now let's actually do this calculation. Okay, so the first version of this that I want to show you is called global alignment. And global alignment is a very simple idea. It basically aligns all of one sequence to all of the other sequence without leaving anything out. Another way of saying that is if something is present in one sequence and not present in the other sequence, you're going to charge a gap penalty for it. So out of our 3 moves, we had the diagonal move, we had the horizontal move, and we had the vertical move, right? So diagonal basically captures match, where you have A aligned to A, and it handles so-called substitution, like A replaced by G, okay? So we're going to have 2 different scores that we're going to have to consider here. So typically we'll have a match score, and we'll have what we'll call a mismatch, okay? And those will just, for our purposes, they'll just be numbers. So I'm going to say match equals +5. Mismatch equals, something like maybe, I don't know, -2. And then horizontal and vertical, so-called indel moves, typically those are also called gaps, basically where something's present in one sequence but not in the other, so there's a gap in the alignment. And there's usually the same score is given to both the horizontal and vertical move. It's called the gap penalty. So let's say that's +5, maybe that's -2. Commonly the gap penalty might be even stronger than the mismatch penalty. So this might be, say, for the purpose of argument, let's just say it's -4, okay? So now what we're going to do is we are going to write the global alignment for our sequences, okay? So the basic process is we are going to fill in the scores one by one. The first thing that I hope that you can see is that when we are aligning some pair of letters, let's say we're going to align the G to the C. So we have 3 possible moves that can take us into that cell, okay? When we consider those 3 possible moves, we need to know which of those is going to yield the highest score up to that point, okay? Remember B to Q, so it's the total score going from the beginning up to that point. So to fill out the score for this cell, we need to have already filled out the score for those 3 cells. To fill out the score for this cell, then I need for those 3 cells, and so on. So evidently the place that I have to begin is just the first letter against the first letter, right? It's the only one where it doesn't depend on any other cells in the matrix, right? Okay, so the global alignment scoring is that we start at the beginning of both sequences by writing basically a 0 as the initial score for basically not aligning. We haven't aligned anything against anything yet. Now, the next thing that we have to write down is, what if we were to skip some of these letters in one sequence before starting to align it to the other sequence, okay? So those in global alignment require that we apply our gap penalty, okay? So I call this my so-called gap penalty. All right, so in practice, what that simply means is we just multiply our gap penalty going along here, okay? So -8, -12, minus 16, minus 20, minus 24, and so on, okay? And we do the same thing going up here. And so on. Okay, now we're ready to fill out our first cell. Why? Because we've got the 3 cells that it depends on, okay? So now we're going to have 3 possible moves that will get us to this cell. So let's consider the 3 possible moves. So let's consider the diagonal move. The diagonal move will align the A to the A with a score of plus 5. It's coming from a cell whose score is 0, so the total score for that move is 0 plus 5. In other words, a total score of 5. We can see right away that that's going to be bigger than the score that we would get for any of the other moves, because that's just going to be minus 4 plus another minus 4 for, in this case, a horizontal gap. So it's going to be minus 8. Plus 5 is bigger than minus 8. So we write down plus 5, and we indicate that that's the move that gave us that plus 5. Okay? So at this point, I think you can see it's a little bit arbitrary how we proceed to fill in the rest of the matrix in terms of the order. For example, we could do it by filling out rows. Okay? So now I can fill out this cell. Why? Because all the 3 cells that it depends on are already filled out. And then once I filled that one in, I can fill that one in, and so on and so forth, but filling it in by the row. Okay? Alternatively, I could go up by column, right? Because now I could fill out this cell because all 3 of its dependencies are also filled in. So I can get that cell. Once I've got that cell, I can fill out that cell, and so on. Okay? Order is kind of arbitrary. But let's go on. We'll do this by rows. Okay, so my possible moves here, horizontal, diagonal, vertical. The horizontal looks pretty good, right? Because it's starting from plus 5. So plus 5 plus a gap penalty of minus 4, that's still going to give me positive 1. Whereas if I take a diagonal move, I'm going to be getting a mismatch score of minus 2, starting from a score of minus 4, that's going to sum to a score of minus 6, right? So I'm going to take the horizontal move, and that gives me a score of plus 1. Make sense? And now I can go on in this way that I'm going to get a score of, for the horizontal, it's just going to be minus 4 plus 1 gives me minus 3 versus a diagonal of G versus an A, it's going to be a minus 2 plus minus 8 would be minus 10. Even worse if I do the vertical. So again, I'm still going to be going along here horizontally. So I think what you can see is once you start getting some strong positive scores in the matrix, the other moves around them tend to all want to come from that spot because it gives you a better score than your alternatives. Okay? So you can see we just fill in the whole matrix here. Just for the purpose of argument, why don't we cut this problem down to a small problem. So maybe we'll align just those 3 letters versus those 3 letters so we don't have to fill out this entire table. So A versus A at this position, the diagonal will be minus 4 plus 5. That's going to give me a positive 1. Whereas if I go horizontal here, it's going to be minus 8 plus minus 4, giving me minus 12. Sorry, what did I do? Oh, no, I'm screwed up. So here, so the diagonal is going to be minus 4 plus 5, giving me positive 1. Or I could go vertically, and that's going to be minus 4 plus 5. And now this is interesting, right? We've got a tie. We can get plus 1 either diagonally or vertically. So the rule is for standard dynamic programming like this, you got a tie. It actually doesn't matter which path you choose. All this guarantees is we're going to find a path that's greater than or equal to the score of any other path. There might be another path that's exact same score. That's okay. All right. So basically arbitrary, you can take either one. So if you want, for variety, we'll take the vertical move, and that's now a score of +1. We do here, we've got 2 cells that we can come from. 1 plus -4 will give us -3 on either the horizontal or the vertical, and the diagonal is going to give us 5 plus -2, which give us +3, which is definitely a better score. So we choose the diagonal, and we get a score of 3 there. Going on to the last position here, we've got A versus G. We can do the horizontal move, and that's going to give us 3 plus -4 give us -1. As we do the diagonal, or we're going to again get 1 plus -2 is going to give us -1, so another tie. Okay, and then the gap is going to be even worse. So again, sort of arbitrary. We can take one of our ties, and that's going to give us the -1. Okay, we've just got one more row to fill out here. So A versus G, I think both the horizontal and that are going to be pretty bad. It's going to be -10, whereas we've got a +1 here, so we can do the gap to that. So it's going to be 1 plus -4 is going to give us -3. Now the C versus the G, we've got this +3 down here, so we do 3 plus -4, that's going to give us -1. Whereas if we do 1 plus -2, it's going to give us -3. So the vertical is going to be bad, so it gives us -1. And finally, we've got this G versus G. And so we're going to take, on the diagonal, we're going to get a 3 plus a 5, gives us a +8, which is clearly better than either the horizontal or vertical moves. At this point, we're now done with the matrix. We've filled out the whole matrix for this 3x3 alignment case. The rule in global alignment is you always backtrack from the opposite corner. Okay? Remember, it's an end-to-end alignment. It goes from the origin corner to the end corner without leaving anything out. Okay? That means everything in each of our sequences is considered in the score. Okay? So that means, by definition, in global alignment, we always start our backtracking from that opposite corner, and we just follow the path that got us there. So that was diagonal, diagonal, diagonal. That means our alignment is just ACG versus AAG, and the common way of writing an alignment is to write the aligned letters in vertical registry with each other. And sometimes, if you want, you can also indicate basically where you've got matches by drawing a line. And you'll see here, they're aligned to each other. It's called as basically a substitution, right? It's not an insertion or deletion, even though the letters are different. It's called as a substitution, okay? So that's global alignment, so-called dynamic programming alignment algorithm applied to pairwise sequence alignment. Any questions about the actual practice of this? Okay, well, why don't we take a 5-minute break and resume, let's say, at, I don't know, 1:22, 1:23, and we'll do some basic questions about this, and we'll continue on Wednesday talking about some other slightly different flavors of alignment. Okay?